Okay, we were looking at chirality in acyclic compounds. Let's look at chirality in cyclic compounds. Okay, so let's just take a simple example here with a single monosubstituted cyclohexane. Again, this could be any group of methyl, chlorine, or bromine, whatever. Okay, this is a chiral. It contains an internal mirror plane of symmetry that cuts the molecule in half. I'm not sure if I can draw this, okay, but basically it cuts the molecule in half. So it has a mirror plane of symmetry. It being achiral, this is optically inactive. Okay. Let's look at another example. In this case, the two arms of the ring are the same. So what I'm going to do is make the two arms of the ring different. You can do that by adding another substituent out here, or you could put a double bond out here. Now, in terms of assigning priorities, the arm with the double bond is more important than the arm with the single bond. So again, we can assign priorities here. If I'm looking at carbon versus carbon versus carbon, that's all a tie. The hydrogen is obviously the lowest priority. The carbon with the double bond is the highest priority. This arm of the ring is next, and then the methyl is third. So 1, 2, 3, counterclockwise S, and the lowest priority is pointed away from me. This is S. And again, what you want to look for is that the two arms of the ring are different. Therefore, it is chiral. I've got 4 different groups attached to that chiral carbon right here. Now, in this case, the two arms are the same. And again, there's different ways to make the arms different. You can put a chlorine or a bromine or something out here, okay, that makes that arm different than this arm. Excuse me. However, if you put the substituent on the number 4 position here, then the two arms would be the same. So that doesn't help you any. Okay, so chirality in cyclic compounds. Let's look at cyclic compounds with 2 or more chiral centers. Okay, and we've looked at cis and trans 1,2 dimethyl cyclohexane. So I'll do the cis right there, and I'll do the trans over here. Okay, the cis, again, I can do these with methyls or bromines or chlorines or whatever. I'm going to do this with methyls. So the cis 1,2 dimethyl cyclohexane. Okay, this exists as we've seen, axial and equatorial. You can do the ring flip and it becomes equatorial axial. The trans we've seen, and I'm not going to write the full name out there again. If it's trans 1, 2, it's real easy to see that it can be diaxial. You do the ring flip, it becomes diequatorial. Okay. Now on the cis, there is an internal mirror plane of symmetry that essentially divides the molecule in half right there. So here's my mirror plane. Now, because it has a mirror plane, so it has a mirror plane of symmetry, that tells you that it is achiral, even though it contains 2 chiral centers. There's a chiral center there and a chiral center here. So it's a mirror plane of symmetry. It is an achiral molecule with chiral centers. Therefore, it is a meso compound, and it's superimposable on its mirror image. Okay. Now let's assign R and S to this chiral center here. Okay. This arm of the ring is substituted, so it has a higher priority than this arm, which beats the methyl. So 1, 2, 3 is clockwise R. The lowest priority is pointed away from me. This one is R. If I take this chiral center, this is the more important arm, okay, then this, and then the methyl. So 1, 2, 3, excuse me, 1, 2, 3, counterclockwise S, the lowest priority is pointed away from me. It is SR, excuse me, and it is meso. Again, we don't say SR or RS because if I'm numbering this direction, it's 1S, 2R. If I'm numbering this direction, it's 1R, 2S. So it's neither, it is meso. So the cis exists as a single meso compound that is superimposable on its mirror image. In other words, if I draw the mirror image of this, okay, or I use, again, wedges and dashes, these are the same molecule. They are superimposable, so they are the same molecule. Again, if it's got an internal mirror plane of symmetry, it's going to be superimposable on its mirror image. And since it is meso, this molecule is optically inactive. So the cis isomer is optically inactive. If you look at the trans, now the trans can exist as, again, two different conformers, diaxial or diequatorial. There is not a mirror plane of symmetry. And it exists as two enantiomers. That is, non-superimposable mirror images. Let me draw the mirror image of this. Okay, so this is coming up and this is going down. Sorry, a little sloppy. Okay. You can see that one is a reflection of the other. Okay, I could also draw this like this. One up, one down. The other one up, and the other one down. Now these two are the same. If I take this one and rotate it 180 degrees in the plane of the paper and set it down there, those are the same. So again, two different ways to represent this as mirror images, a reflection, and then this swap, the chirality. Now let's assign priorities here. This arm beats that arm, beats the methyl. 1, 2, 3, clockwise R. Lowest priority is pointed away from me. That is still R. Again, if I'm looking at this chiral center, this arm beats that arm. 1, 2, 3, counterclockwise S. Lowest priority is pointed toward me, so I swap the chirality, that becomes R. If I'm confident in that, these become SS, but let's just check that. Okay, so the chirality here, this arm beats that arm, beats the methyl. 1, 2, 3, counterclockwise S. Lowest priority is pointed away from me, it's still S. If I look at this chiral center, this arm beats this arm. 1, 2, 3, clockwise R. Lowest priority is pointed up toward me. So again, I swap the chirality, that is S. So I've got RR versus SS. Again, one way that you can recognize meso compounds is their symmetry, and they're always going to be RS or SR. Your enantiomers are going to be RR versus SS. Okay, now that's our cis 1, 2. And trans 1, 2, let's look at cis 1, 3 and trans 1, 3. Okay, cis, and I'll go ahead and draw the other one here with dashes. Okay, wedges and dashes, and these are the same molecule. The cis 1,3 exists as a meso compound. Okay, again, this is achiral because there is an internal mirror plane. Okay. Again, if these are on the same side in terms of conformations, okay, these can both be diaxial or di-equatorial. Again, the di-equatorial is the more stable, again, in the chair conformation. If you're looking at this, again, here's your mirror plane of symmetry. It cuts right through the molecule, okay? And again, likewise right here. So the cis exists as a single meso compound that is optically inactive. So again, this is meso. It's an achiral molecule with chiral centers. Okay. And it is optically inactive. If you look at the trans 1,3, again, it can exist as a pair of enantiomers. And I'm going to draw these as the mirror image. So this is your trans 1,3. And again, this is chiral. There is no mirror plane of symmetry. Therefore, we have a pair of enantiomers. And these are optically active. If you had a racemic mixture of the two, then their optical activity would cancel one another and they would have no net optical activity. Let's assign R and S to this. This arm has a branch, so it's more important than that arm. So 1, 2, 3 is clockwise. Lowest priority is pointed away from me. That is R. If I look at this position, this arm is more important than that arm. So 1, 2, 3, counterclockwise S, the lowest priority. The hydrogen is pointed up toward me. Again, that becomes R. So that's your 1R, 2R, and by analogy, this is your 1S, 3S. So 1R, 3R, 1S, 3S, if I said that wrong. Let's look at our cis 1,4. They're both up or down, okay? And these are superimposable, though, so therefore they are the same, okay? And one of these would be axial, equatorial, and you do the ring flip and you get, again, equatorial, axial. There is an internal mirror plane of symmetry. Actually, I have two of them. There's one that cuts right through that direction and one that cuts through this direction. So in fact, the cis 1,4, dimethyl cyclohexane, again, these could be any of the two same groups, okay? This is going to be achiral because it has, again, a mirror plane of symmetry. And it is optically inactive. Notice, this is not a chiral center. This arm is exactly the same as this arm. So I don't have a chiral center, so I really don't want to call this a meso compound because a meso compound is an achiral molecule with chiral centers. Notice that there are no chiral centers at all on this molecule. Okay, let's look at the trans. So the trans 1,4 Again, if you build a model of this, you can see that easily this is diaxial. You do the ring flip, it becomes di-equatorial. And I'm sorry, I left off up here that this is axial equatorial. You do the ring flip, equatorial axial. Okay, we've been through all this. So the trans 1,4 is again achiral because there's a mirror plane of symmetry. And this mirror plane cuts through right here. Okay, now I don't have the one that cuts through here because this one is up and that one's down, but I do still have this mirror plane of symmetry. And notice it's achiral. This is not a chiral center. This arm is the same as this arm. Okay, so it's achiral because it has a mirror plane of symmetry and it is optically inactive. And so again, there are no chiral centers for the cis or the trans 1,4 disubstituted. Okay, so again, it's best to evaluate these as to whether they have a mirror image or not in the planar structure rather than the chair conformation. Makes it a little easier to determine that. The last thing I need to talk about is, again, optical activity and enantiomeric excess, EE. Enantiomeric excess. Again, we've defined a racemic mixture as being a 50-50 mixture. So I got a 50-50 ratio of the R isomer to the S isomer. I don't know if the R isomer is dextrorotatory or levorotatory, but I do know that the S isomer would be opposite in direction, but the same magnitude, and so there would be no net optical activity. So no net optical activity. Again, because they cancel. Now, there's this concept of enantiomeric excess. If one of the enantiomers is in excess of the other, the difference is explained as the enantiomeric excess. Spell that, sorry. Enantiomeric excess. Again, this is just the percent of one isomer minus the percent of the other isomer. So the enantiomeric excess of a 50-50 mixture is 0. 50 minus 50 is 0. Okay, let's say we had a 60% of the R isomer and 40% of the S isomer. 60 minus 40 would give me 20. So I have a 20% enantiomeric excess of one isomer over the other. Now, because this one isomer is in excess over the other isomer, this does have a net optical activity. So a net optical activity due only to the excess. Okay? So if I have 60% of the R isomer and 40% of the S isomer, so let's write that down, 60% of the R and 40% of the S. Let me break this down. 40% R plus 20% R. These, the 40% R and the 40% S, cancel. So the activity is due only to the excess, the 20%. That's why we use the enantiomeric excess. And so this can be easily measured by looking at the observed rotation over the specific rotation. What fraction of this do we see? Okay. So if we had 100% of one enantiomer over the other, then this would be unity. Okay, the enantiomeric excess would be unity, 100. Okay, All right, so it's really easy to go this direction. Let's say I've got 80% of the S isomer and 20% of the R isomer. What is my enantiomeric excess? This is real easy. 80 minus 20 gives me 60%. I would expect my optical activity to be 60% of the standard. Okay? Now it's easy going that direction. When I give you the enantiomeric excess and you have to calculate the ratios, so what are the ratios given the enantiomeric excess? This is a little bit more difficult of a calculation, but let me walk this through for you. Okay, so I'm just making up some numbers here. Okay, if you have a 70% enantiomeric excess, that would mean that you would have, again, 85% minus 15% would give you 70%. For instance, if you had an 80% enantiomeric excess, the way you get to 80 is, again, these two values have to add up to be 100. So 90 minus 10% would give you, again, 80%. Okay. So take this value minus that value to give you the enantiomeric excess. So let's say we had a 90% enantiomeric excess. That would require 95% minus a 5%. So that would give you a 90%. So again, if this is one isomer, this is the other, 5% of this is canceled by the other. So you only get 90% of the optical activity.